This paper is titled Polynomial Time Byzantine Agreement with Almost Optimal Resilience. This is a classic problem in distributed computing. In the Byzantine agreement problem, there are n processes. Initially, each process holds a single bit, which we're going to think of as being plus or minus 1. And what makes this problem subtle and interesting is that the processes can obey the protocol that we give them or possibly be corrupted by the adversary and behave arbitrarily, also known as Byzantine processes. So in this problem, the goal of each process is to eventually decide on a output value subject to these two criteria. So the first says that they should all decide on the same value, either plus or minus 1. And the second says that there's no trivial solution to the first one, meaning you can't just ignore your input and all decide 1. You have to choose a value that's originally held by at least one of the players. Okay. So these protocols are measured in different axes. Time or latency is one of them that we'll get to, and resilience is the other. So resilience is the number of processes that can become corrupted by the adversary and have the remaining processes still finish the protocol correctly. Okay, so in this model, communication is done by point-to-point messages. The message delivery is asynchronous. So when a process issues a message, it will eventually be delivered, but there's no specific maximum time of delivery. So the adversary is completely in control of the order in which messages are delivered. And latency in this model is a little subtle to define, but latency is measured by the maximum length of a chain of dependent messages. Okay, so as I said before, the adversary controls the order of message delivery. And in addition, it can adaptively, i.e. dynamically, choose to corrupt up to F processes, where F is a parameter. So the adversary in this model is all-knowing. It can see the internal state of all processes and then use this information to choose when and whom to corrupt. Okay, so in this model, there's some well-known impossibility results. So Fisher, Lynch, and Patterson in '83 showed that if your protocol works in this asynchronous model and is deterministic, then you can't solve Byzantine agreement even if one process fails and stops. So it doesn't behave arbitrarily, it just stops working. So it neither sends any messages. There's several proofs in this model, in fact, stronger models, that you can't tolerate more than n/3 corrupt processes, even if your protocol is randomized. So in the specific model that we're looking at, asynchronous with arbitrary message delivery, this is basically a trivial proof. And in more restricted models, like synchronized models, it becomes non-trivial, and that's where most of the proofs are. Okay, so the early work on this problem in the 1980s by Ben Orr and Bracha showed that this problem actually is solvable in the randomized asynchronous model, but with exponentially long latency. So the protocol terminates correctly with probability 1, but its expected running time is exponential in n. So Ben Orr's protocol had a resilience all the way up to at most n/5. And Bracha improved Ben Orr's protocol to have the optimal resilience up to n/3. Okay, so that was the state of the art for a long time. And about a decade ago, King and Saya came up with a new protocol, a new way of doing this that could have resiliency linear in n, but still with a pretty low constant coefficient in the resiliency. So they came up with two protocols. One, the processes have an internal computation that takes exponential time, but this doesn't affect the sort of distributed latency, and it could tolerate up to n/400 corruptions. And they had a fully polynomial time algorithm, polynomial latency and polynomial local computation time that had resiliency about n/1 billion. Okay, so the new result in this paper is a new Byzantine agreement protocol that gets pretty close to the optimum level of resiliency. So F up to n/4, polynomial latency, polynomial local computation. Okay, so there's been hundreds of papers on Byzantine agreement. Some are practical, some work in different models. There's very little work in the specific model that we consider, but if you weaken any of these constraints just a little bit, then you can have different protocols. So for example, if your network is synchronous, then you can solve Byzantine agreement with a deterministic algorithm. Takes f+1 rounds, which is optimal, and f can be as large as n/3. Okay. If you assume that your adversary is computationally bounded, then cryptography becomes useful. And using this cryptographic primitives, you can actually solve Byzantine agreement in optimal constant latency with f all the way up to n/3. Okay. So one of the assumptions we make is the adversary can choose, in the middle of the protocol to take over one of the players, one of the processes. And this is called an adaptive adversary. So if you assume that the adversary has to corrupt all the players it's going to corrupt at the beginning of the protocol before it begins, then you're talking about a non-adaptive adversary. And here you can get some other interesting results. So in the synchronous model, you can have resiliency almost up to n/3, a little bit below n/3 plus epsilon in a logarithmic number of synchronized rounds. And even in the asynchronous model, you can get close to n/3 resiliency. This last protocol by Capron et al., it's Monte Carlo. So the failure probability means that the protocol could either deadlock or not reach or terminate, but without agreement. Okay. So our algorithm and King and Saya's algorithm are both based on Braca's algorithm. And Braca's algorithm basically reduces the problem to coin flipping, okay? And we have different ways to implement this coin flipping primitive. So let's look at Braca's algorithm. Braca's algorithm itself is based on Ben Orr's algorithm, and it has two useful innovations that make it much easier to think about the space of adversarial strategies. So the first idea is even though the underlying communications network is point-to-point, Braca shows how to implement a certain reliable broadcast primitive that guarantees the following. So if you want to broadcast a value V and you obey this reliable broadcast protocol, then all the good players, that is the non-corrupt players, eventually will accept that V was the value that you broadcast, and they will not accept any other value. And if a corrupt process tries to initiate a broadcast, it can't create a situation that's inconsistent. So it can follow the protocol, and everyone will, all the good players will accept the same value, and it will look like a sort of normal broadcast. Or if it tries to cheat too much, the good players will accept no value. So it's impossible to create a situation where some population of good players accepts a value and some population doesn't. Okay, so one subtlety here is that because the network is asynchronous, there's no guarantee on the time to completion. These protocols complete eventually, but there's no timeout period where you can assume that a message has not been delivered. Okay, the second of Braca's innovations was a validation mechanism. And here the idea is that once a player is corrupted, in principle, it can choose to not follow the protocol anymore. It can have internal state transitions that just don't correspond to the normal state transitions of the protocol. But this validation mechanism says that actually without loss of generality, we can force corrupt players to follow protocol. And specifically, whenever a player sends a message, you do not validate that message until you have received accepted broadcasts from enough other players that would explain why that player sent you the message. In other words, you have to validate that player got a plausible set of messages that would have caused it to make state transitions and send you the given message. Once you take into account these two things, the adversary's space of strategies are highly restricted. So it still has the power to schedule messages adversarially. And in the corrupt processes in which it is taken over, they have to follow protocol, but they can choose their coin flips maliciously. Okay, these are randomized processes and they can decide how the coins come up, heads or tails. Okay, so how Broca's algorithm works, it executes the following loop indefinitely, 3 steps. Initially, every player into this loop holds a value, which is a single bit, plus or minus 1. And the first step is everyone broadcasts their current value to everybody else. Every process needs to entertain the possibility that F other processes have crashed, so it can't move on if it waits for every process to send it a message. So as soon as a process receives n minus F messages from other processes, then it must, move to the next step of the algorithm, because that's all it can count on. So at this point, every process updates its value to be the majority value of the messages that it's seen. In other words, you take the sign of the sum of the other messages, and then you move on to step 2. Okay. So the important takeaway from step 1 here is that if you happen to have a situation where all the n minus F non-corrupt processes hold the same value, then that means that they will actually be a majority in any set of n minus F messages, because F is strictly less than n over 3. And in this case, everybody who gets past step 1 is going to set their value to be the supermajority value. Step 2, you send your value out again, wait for n minus F processes to send their value. And at this point, you see if there is a strict majority value called V star. That is a value that is represented among at least greater than n over 2 of these messages. If there is a strict majority value, then you update your value to be this quantity decide V star, meaning you're willing to end the protocol in the next step and decide V star if step 3 goes well. Okay, so this just shows a willingness to end the protocol, and it shows that you've seen the majority value. Okay, step 3, send out your value again, wait for n minus F other processes to send out their value, and now you count how many of these decide V star messages do you get. And depending on this number, you do one of 3 things. So if XP is not 0, if it's at least 1, then you know what the majority value is, and you set your value to be the majority value of V star. And this is what your value will be going into the next iteration of Broca's algorithm. If XP is at least F plus 1, then you can commit to deciding V star. You know that this is going to be the output of the vertical, and you can decide V star. And if XP is 0, that is, you're in the third case here, then you choose your new value on the basis of a private coin flip. So you just flip a coin, choose plus or minus 1 with probability 1/2. Okay, so if P is aware of the majority value of V star, it'll keep this value going into the next iteration. And the good case here is these XP values never differ by more than F between 2 good processes. So what that means is that if any player is deciding V star, that means every other player has to either also be deciding V star or be in the case 1 where it's committed to V star. But either way, there's unanimous agreement that V star is everyone's value. And in the next iteration of Broca's algorithm, they will all decide this value if they haven't already. Okay, so that's basically the end game of the algorithm. The more standard case is some population has seen the majority value of V star and is keeping it, and the other population is flipping coins. Okay, so how do we want this coin flip to go down? Okay, so what we really want is every player should flip their coin, and we are optimistic that what they're going to do is flip V star. If this happens, then everyone's in agreement, and once again, everyone will decide V star in the next iteration of Baraka's algorithm. But the probability of that happening if everyone flips private coins is exponentially small. That's why the latency of Baraka's algorithm and Ben Orr's algorithm is exponentially small in n. So what we really need is a different type of coin flipping protocol, collective coin flipping, where all players will agree on the output of the procedure coin flip. So they're sort of flipping a global coin. And ideally, the outcome here is unbiased. Unbiased, even if up to F players are participating in this coin flip protocol maliciously. Okay. So if we had such a protocol, this would be great news because we could just plug it directly into Baraka's algorithm. And every time we go through an iteration, there'd be a 1/2 probability of everyone reaching, agreeing to the majority value and terminating in the next iteration. So we need log n iterations in total with high probability. This is a little bit too good to be true. We don't, know of any such protocol with exactly these specifications. So our strategy following King and Saya is to do the following. So we want to have a coin flipping protocol where if the parties cheat and bias the coin flip or create disagreement on the outcome of the coin flip, then that's called fraud, and we will detect fraud and know at the end of running this protocol some number of times who the fraudulent parties are, who the corrupt parties are. And if we knew who the corrupt parties are, we could ignore their opinions going forward and remove their influence from this game. Okay, so let's look at a simplified coin flipping game that's a little bit simpler than the one that we study in the paper. Okay, so in this coin flipping game, we're going to assume that there's n players, and at the beginning, exactly f of them are corrupt for some fixed set of f players, which we don't know. Okay, so the game proceeds in rounds, and the way each round goes is as follows. So before the round begins, the bad players choose an outcome for the coin flip that they want to create. Okay, so it doesn't really matter how they choose this. They can choose it randomly, deterministically, it doesn't matter. So but they choose an outcome that they want to commit to at the beginning, plus or minus 1. Every good player flips a fair coin, xi, and announces its outcome simultaneously. And the bad players are, let's say, infinitesimally faster than the good players, and they see the outcomes of the good players, and then based on what the good players announced, they announce their own, coin flips, which they chose, deterministically or as they like. Okay, and then we check to see what the sign of this sum is. If the sign of the sum is in fact sigma, which they predicted it would be, then they win. And we go on to the next round. So the nominal goal of this game is to have the sign of the sum not be sigma, but the adversary can pretty much always guarantee that doesn't happen. So the real goal of the game is slightly different. The real goal of the game is we play this for some number of rounds over and over and over again. And then we look at the transcript of what everybody, what everybody's messages were. And we try to declare a player bad at the end based on the transcript. Okay, so here's a run through of the algorithm. Let's say there's 10 players, 1 through 7 are good and 8 through 10 are bad. So the bad players say the outcome of the coin flip is going to be -1. The good players flip their coins. Bad players see these, choose their own coins, and make the sign of the sum negative. Let's say sigma is -1 again. So the good players flip their coins, the bad players come in, see these, choose their own coins, and make the sign of the sum negative. And then they choose sigma in round 3. Bad players flip their coins, good players come along, good players flip their coins, bad players choose their coins so that the sign of the sum is positive, and so forth and so on. Okay, so in this case, t would be 3, but t is going to be a very large number. And we play this game for t rounds. And then you look at the entire, sort of history of what you see here, the columns and the rows, and you say, who is not flipping fair coins? Okay, so you can think of this as sort of a random walk on a line where the each contribution of a player contributes +1 or -1. And let's say, think about these possibilities here. Sigma, let's say, is -1. That's what the adversary wants to happen. And let's think about the aggregate contributions of the good and bad players. So SG is the sum of all the good coin flips, and SB is the sum of all the bad coin flips. And if SG is negative, then the adversary is happy, and it can do anything at once. It can set SB to be 0, which doesn't look very suspicious, and it's happy with the outcome. If SG is positive, then the adversary is forced to act, and it needs to push the sum in less than 0. So in this case, the absolute value of SB has to be at least as large as the absolute value of SG. And as a consequence here, we can look at the second moment of SG, and this is a sum of lots of terms whose expectations are 0 because the coin flips are independent, and the only non-independent non-zero expectation terms here are the xi squareds, which add up to n minus f. Okay. On the other hand, if you look at SB, what it's forced to do, half the time SG is, let's say, consistent with sigma and nothing, and then half the time the absolute value of SB has to be at least as large as the absolute value of SG. So what do we know about SB squared? It must be at least 1/2 n minus f in expectation. Okay, so we played this game for t rounds, and what we're going to do to detect fraud here is measure pairwise correlations between two players. So the correlation score for I and J is the inner product of I's coin flips and J's coin flips over all t iterations. So what do we know about good players? In expectation, their correlation is 0 because they're flipping independent coins. And by Chernoff bounds, the correlation never deviates too far away from 0, about square root of t. On the other hand, bad players are doing things slightly differently. So what do we know about SB squared? SB squared is, by the arguments before, for each of the t rounds, it's at least 1/2 n minus f in expectation. Okay, and it'll be very close to this with high probability. And we can decompose SB squared as a bunch of correlation scores here. Okay, so the xi squareds contribute some amount, which we can calculate here, and the xi times xj terms all add up to the correlation score of I and j. Okay, so we have a lower bound on SB squared, and that translates into a lower bound on the sum of the correlation scores. So we can say that the maximum correlation score is at least the average, and we have a good lower bound here on the average. Okay, and this means that there exists at least one bad pair of nodes whose correlation score is bounded away from 0 by this epsilon. Recall that the number of bad players is n over 3 plus epsilon. So epsilon sort of controls how has to do with how many bad players there are. Okay, and these arguments here really depend on f being bounded away from n over 3. Okay, so to summarize, the good correlation scores are all controlled by these Chernoff bounds, and they're not too far away from 0. And we know that there exists some bad correlation, which is at least epsilon t over n. And in general, these two bounds are incomparable. But for t sufficiently large, the second is going to dominate the first, and that's what we want to do: is set t to be sufficiently large. Okay, so when we set t to be about n over epsilon squared, then we can say that there's at least one bad correlation that dominates all good correlations. And there's nothing much we can say about good bad correlations. So if we think of this as a big weighted clique where you weight an edge based on its correlation score, then not much is going on the clique of good players. They just have very noisy correlations close to 0. The clique on bad red players is possibly significantly higher. and there's almost nothing we can say about any specific edge crossing the cut. So these could have very large correlations in general. So what does this mean? This means that if we take the maximum correlation score between two players, let's say between players I star and J star, at least one of them will be bad. Okay, so in our protocol, because the good players begin with a majority, it's fine if we blacklist both I star and J star, because blacklisting good players and bad players at the same rate retains the good players' majority. Okay, so the real coin flipping game is a bit more complicated because of asynchrony. Xi is not a coin flip, but it's a sum of coin flips. We can organize these coin flips using king and size blackboard primitive. So in this blackboard primitive, player I flips a series of m coins and writes them to the ith column in this sort of imaginary blackboard matrix. You can't really be sure of filling up this matrix because f players might crash halfway through. So a full blackboard is one with n minus f full columns, and the rest of the columns might be partial. And because the scheduling power of the adversary is pretty strong, it can make sure that everyone agrees on the contents of this blackboard except for possibly the last entry of every partial column. So two good players can disagree on the contents of the blackboard. So if xi is the sum of the ith column, we can say xi superscript p is sort of what p thinks the ith column is. Okay, so now instead of just summing up a single vector of coin flips, it sums up all the coin flips on the blackboard that it sees, takes the sign of that, and declares that the outcome of the coin flip, the global coin. So obviously, because two players can see slightly different blackboards, they can actually think the coin came up different with opposite signs, and that can create disagreement between good players. So what do we want to happen? Because the sum of two good players can be off by most f, we want this to be a relatively negligible quantity. So if we have on the order of mn coin flips on this blackboard in total, the standard deviation is about square root of mn. The true sum is sigma. Then every player sees some sigma perturbed by up to f. So inside this interval, if this interval contains 0, then we're in trouble because the adversary can put some players to the left of 0 and some players to the right of 0 and create very easy disagreements on the outcome of the coin flip. So we want this to be a relatively rare occurrence, and what that means is that we want f to be substantially smaller than a single standard deviation, so m has to be much larger than n. Okay, so the goal of the coin flipping game is to figure out who's not playing correctly. So the goal is we're going to run an epoch for t iterations. And the goal of this epoch is to get to the end and figure out who is not playing correctly and reduce their weights accordingly. So initially weights are 1. They're always in the interval 0 to 1. And the purpose of the weights is to judge the trustworthiness of their coin flips. Okay, so if xi has certain coin flips, we're going to weight them according to wi when we calculate the sign of the sum of everything on the blackboard. So because we have weights, correlation scores are naturally weighted, and for reasons that might become clear in the calculations, we also keep track of deviation scores, which only apply to a single player, and we're just measuring the second moment of the weighted sum of the coin flips issued by player I. Okay, so from the simplified coin flipping game, where n was bounded away from n over 3, the resilience drops to n over 4 plus epsilon because the scheduler can basically not schedule messages from f good players, and there's no way to distinguish that from crashes. So the resilience of the protocol drops to n over 4 plus epsilon. Okay, so what do we know about good player scores at the end of an epoch? A single good player's deviations is well behaved. 2 good players' correlations are well behaved, and the limits are controlled by Chernoff bounds. And we can set these thresholds alpha and beta as being sort of the outer limits of what a good player or 2 good players might plausibly give us in terms of deviation or correlation scores. We can also do similar calculations and get the average of the bad players' scores at the end of an epoch. And here, this is the gap lemma here says that if we take the deviation scores of all the bad players and we take the pairwise correlation scores of all the pairs of bad players and subtract off these allowable thresholds, you know, alpha and beta, that this is still bounded away from 0 by some quantity that's linear in epsilon here. Okay, and if you what this means, of course, is that at least one deviation score, or at least some correlation score, is much, much larger than it should be, assuming the players were all good. Okay, so we have the same problem here. We have a clique. The edges crossing the clique we don't know much about. The clique on the good players is all 0. The clique on the bad players, it has at least one large edge somewhere. And how should we reduce the weights? So we're going to give each vertex a capacity, which was its former weight, you know, before the epoch ended, and its new weight is going to be its weight going into the following epoch. A loop, the weight of a loop depends on its deviation score. The weight of an edge ij depends on its correlation score. And we know that all the edges involving 2 blue good players look fine, and they have 0 capacity. Okay, so whenever we see an edge with positive capacity, we know that one or both of the endpoints is bad. Okay, so one reasonable way to deduct weights is because of this, at least one endpoint being bad property holds everywhere, we can just find a maximal matching in the subgraph of non-zero capacity edges and blacklist all the endpoints of this matching. That is, set their weights to 0, removing their influence on the coin flipping game entirely. The good news here is that the weight of the good players and the weight of the bad players maintains this 3 plus epsilon to 1 weight advantage because we're docking them at the same rate, basically. The negative is a little subtle. It's that because everyone sees slightly different scores and therefore they see slightly different weighted graphs, they might blacklist different sets of players. And if 2 players blacklist different sets of players, this is an annoying thing to deal with because it can induce disagreements down the line, which we don't like. So our solution is to use a fractional matching algorithm to control the blacklisting. So we use a very specific rising tide algorithm with a continuous Lipschitz property. And then we use this fractional matching in the same way that we would an integer matching and fractionally blacklist nodes. So now, because we're doing fractional blacklisting, the weight sort of drops from 1 towards 0, but possibly not all at once. So someone's weight can be some fraction between 0 and 1. Okay, so what we prove here is a Lipschitz property for this natural fractional matching algorithm, which means that small changes to the input, that means small changes to the weighted graph, induce small changes in the output. So there's greedy maximal matching algorithms and greedy fractional maximal matching algorithms that don't have this property. So we look at one that does. Okay, so we prove this theorem to the effect that if A to V and A to E are the amount by which 2 graphs differ in their vertex and edge capacities, then the output of this algorithm at any point is linear in A to V and A to E. Okay, so the invariant we maintain here is that the rate at which we dock the good players' weights is no faster than the rate at which we dock the bad players' weights up to a pretty small negligible error. And this stems from the fact that everyone is looking at slightly different weighted graphs when they're doing the weight reduction. Okay, but the good players begin with a 3-to-1 weight advantage, and they maintain this weight advantage throughout the protocol. So we can treat that as an invariant. Okay, so the point of this is to get the bad players' weights to go to 0. Once the bad players' weights go to 0, then the protocol finishes naturally, very easily. Because the scheduling power of the adversary, which never goes away, is not strong enough to keep the good players going indefinitely. Okay, so the total latency of our protocol is polynomial, but kind of large. So when epsilon is constant, it's n to the fourth. When epsilon is, very, very close to 1 over n. So if you want like f strictly less than n over 4, but that's it, then this is closer to n to the 8th. So there's a significant room for improvement in the latency, and there's also room for improvement in the resiliency to get from f less than n over 4 down to f less than n over 3.